What does it mean to know something in physics? At first glance, the answer may seem straightforward. Knowledge in physics is built from careful observation, precise measurement, and the steady accumulation of facts. Yet, as we look closer, the picture becomes richer and more nuanced. Physics is, at its core, the study of matter, energy, and the universe itself. The journey from curiosity to understanding is guided by the scientific method, a set of principles and practices that have shaped generations of discovery. But this method, powerful as it may be, is not without its limits and underlying assumptions. When physicists set out to explore nature, they do so with a deep trust in the existence of universal laws, patterns and regularities that seem to govern everything from the smallest particles to the grandest galaxies. The assumption that such laws exist and that they are independent of any individual observer underpins all scientific inquiry. However, this belief is itself an unprovable philosophical stance. Physics proceeds on the conviction that an objective reality exists, even though this cannot be demonstrated with absolute certainty. In this way, every scientific investigation is built atop a foundation of assumptions, some so ingrained that we rarely notice them, yet all crucial to the enterprise. The process of building knowledge in physics is often described as a dance between theory and experiment. Theories, like the Standard Model of particle physics, provide frameworks that organize ideas and make predictions about the world. Experiments, in turn, put these predictions to the test, offering evidence that may support or challenge existing models. But theory and experiment are not separate forces. They are tightly intertwined, each guiding and shaping the other. Theorists often rely on experimental results to refine their models, while experimentalists look to theory to decide what questions to ask and what phenomena to probe. This mutual dependence ensures that neither can progress far without the other. Yet, the relationship between theory and experiment is not always harmonious. Sometimes, experiments yield results that defy current theories, forcing physicists to question long-held beliefs. At other times, theories predict phenomena that remain just out of reach for experimental confirmation. This tension drives progress, as scientists continually adjust their understanding to achieve closer agreement between what is predicted and what is observed. The process is one of consistent adjustment, where knowledge is not static but evolves as new evidence emerges. Underlying all of this is the scientific method, an approach characterized by skepticism, empirical testing, and a willingness to revise ideas in light of new data. Physicists use hypothesis-testable statements about the natural world to guide their investigations. Through observation and experiment, they gather evidence, then use reasoning to draw conclusions. The claim, evidence, and reasoning framework is a common way of structuring scientific arguments, ensuring that every assertion is grounded in data and logical analysis. But the scientific method has its boundaries. It is inherently empirical, relying on observations that can be tested and reproduced. Some questions, especially those that fall outside the realm of the observable, are not accessible to scientific inquiry. Furthermore, all experiments and theories rest on certain assumptions, such as the reliability of measurement instruments or the constancy of natural laws over time and space. While these assumptions are often justified by prior experience, they are not immune to challenge. Recognizing and testing these assumptions is a vital part of the scientific process, but it is impossible to eliminate them entirely. In addition, the human element in science cannot be ignored. Biases, preferences, and limitations in current knowledge can subtly influence the course of research. Scientific progress depends not just on logic and experimentation, but also on creativity, collaboration, and the willingness to challenge established ideas. Theories and laws in physics are not immutable truths, but evolving constructs that reflect our best understanding at any given moment. They are subject to revision, refinement, and sometimes even replacement as new data comes to light. Philosophers of science have long debated whether scientific theories are simply historical constructions or if they bring us ever closer to some ultimate truth. The interplay between theory and observation, and the interpretive challenges that arise when data and theory disagree, are central to this ongoing conversation. What is clear is that scientific knowledge in physics is provisional, dynamic, and shaped by both the strengths and the limits of the methods we use. Ultimately, the story of knowledge in physics is one of exploration, a relentless quest to uncover the workings of nature, guided by empirical evidence, creative theorizing, and a recognition of our own limitations. While the scientific method offers powerful tools for discovery, it also reminds us that certainty is always just out of reach. In physics, as in all science, understanding grows not from the illusion of final answers, but from the continual challenge and revision of what we think we know. Imagine standing in a laboratory, stopwatch in hand, ready to measure the time it takes for a ball to fall from your grasp to the floor. As simple as this act may seem, it is already intertwined with the fundamental limits of what we can know about the physical world. Classical physics, with all its elegance and promise of certainty, faces unavoidable constraints the moment we try to observe, measure, or quantify anything. This is not just a technical nuisance, it is a profound feature of knowledge itself, woven into the very way we interact with nature. At the center of this challenge lies measurement error, the persistent gap between what we intend to record and what we actually capture. Errors in measurement can arise in many ways, broadly classified as systematic bias or random error. Systematic bias is the consistent slant that nudges every measurement in the same direction. Perhaps your stopwatch always lags by a fraction of a second, or your ruler is ever so slightly warped. Random error, in contrast, is the unpredictable jitter. Those small, irreproducible variations that stem from the quirks of human reaction time, environmental changes, or the inherent imprecision of our instruments. Together, these errors define the reliability of a measurement, offering insight into how much we can trust our results. Physicists have developed sophisticated statistical methods to assess and quantify these errors. They refer to standard error, which gives a sense of the expected spread in repeated measurements, and the coefficient of variation, which relates that spread to the size of the quantity being measured. Limits of agreement describe how much variation is tolerable before two measurements should be considered fundamentally different. These tools are more than mathematical conveniences. They are essential for translating the messy world of experiment into the precise language of physics. Reliability, in this sense, becomes a measure of how faithfully a result reflects the underlying reality. A recognition that absolute precision is always out of reach, but that uncertainty can be defined and understood. No matter how refined our instruments or how careful our methods, some degree of error persists. Even the most advanced measurement tools, machines engineered to the finest tolerances, cannot fully escape the shadow of uncertainty. The limits imposed are not simply technological, but also thermodynamic in nature. Just as heat sets a fundamental bound on the efficiency of an engine, so too does it constrain the quality of information we can extract from a physical system. In classical physics, this thermodynamic limitation has been likened to a form of uncertainty that, while distinct from its quantum counterpart, is nonetheless real. This analogy reminds us that our quest for knowledge always encounters a horizon beyond which clarity dissolves into ambiguity. Yet, paradoxically, it is by pushing against these limits that physics advances. The drive to measure with ever greater precision has led to the discovery of new phenomena and the questioning of once immutable laws. As measurement techniques improve, so does our ability to test the boundaries of established theories. Physical constants, the values that underpin equations and predictions, are refined, sometimes revealing subtle discrepancies that open the door to entirely new domains of inquiry. In this way, the pursuit of precision is not only about minimizing error, but about probing the very structure of physical law. There is also an educational dimension to this landscape of uncertainty. When students engage in experiments, they often struggle with the distinction between accuracy and precision, between the ideal and the achievable. Their reasoning, shaped by both classical and quantum contexts, reflects the broader challenge faced by all who seek to measure and understand. Even self-reported measurements, such as those used in studies of human behavior or physiology, are influenced by unavoidable errors that can ripple through results and interpretations. Recognizing, quantifying, and accounting for these uncertainties is a skill at the core of scientific practice. The limits of classical physics are revealed not only by the breakdowns of its theories in the face of quantum or relativistic phenomena, but also by the quiet, persistent boundaries imposed by measurement. As new experimental techniques and technologies emerge, these boundaries shift, but never vanish. The act of measurement, so central to science, is always accompanied by uncertainty, a shadow that both challenges and inspires. In embracing these limitations, physics remains a living discipline, where the relentless pursuit of knowledge is tempered by the humility of what can and cannot be known. In the early 20th century, as physicists turned their attention to the subatomic world, they discovered a landscape where familiar rules no longer applied. The certainty and determinism that defined classical physics gave way to a new and unsettling reality, one in which the act of observing could not be separated from the phenomena being observed. Nowhere is this more apparent than at the heart of quantum mechanics, where the limits of human knowledge are not simply matters of technical limitation or experimental error, but are woven into the very fabric of nature itself. At the center of these quantum mysteries lies the uncertainty principle, a concept introduced by Werner Heisenberg in 1927 and developed through a blend of insightful thought experiments and mathematical analysis. Heisenberg's famous microscope scenario illustrated the strange predicament physicists faced when trying to determine the position of an electron. The very light used to observe it disturbs its momentum, and vice versa. The uncertainty principle captures this fundamental limit. There exists a minimum threshold for how precisely certain pairs of properties, like position and momentum, can be known at the same time. This is not a statement about the inadequacy of our instruments or the skill of the experimenter. Rather, it is a statement about the impossibility of joint knowledge at the quantum level. No matter how advanced our tools or how ingenious our methods, nature withholds exactness in the subatomic realm. The implications of the uncertainty principle extend far beyond the laboratory. It marks a sharp break from classical determinism where, in principle, every future event could be predicted given enough information about the present. In quantum mechanics, such a vision of total knowledge is fundamentally unattainable. The universe at its smallest scales is not merely unknown, but is, in a profound sense, unknowable in the ways that classical physics once promised. This realization did not simply frustrate physicists, it forced a fundamental rethinking of what it means to measure, to know, and to predict. The observer effect, closely tied to the uncertainty principle, deepens this challenge. In quantum physics, observation is not a passive event. To measure a particle's property is to interact with it, and that interaction inevitably alters the very property under scrutiny. The observer and the observed are entangled in a dynamic where knowledge is gained only at the expense of disturbance. Unlike in classical physics, where observation can be imagined as a neutral process, quantum measurement is always a form of intervention. This means that the boundaries of what can be known are set not just by the sensitivity of our devices, but by the unavoidable disturbance that observation itself brings about. As physicists probed deeper, they found that these quantum effects do not simply reflect gaps in our technology or cleverness. They reveal intrinsic features of reality. The impossibility of jointly measuring incompatible quantities, such as position and momentum or different components of a particle's spin, is not just a practical hurdle, it is a fundamental boundary. Recent research has even produced mathematical theorems that set precise limits on the kinds of knowledge quantum systems can yield, and some thought experiments have raised questions about whether quantum theory can consistently describe itself without paradox. The result of all this is that the quantum world is not only indeterminate in practice, but indeterminate in principle. The outcomes of quantum events are governed by probabilities, not certainties. Even with perfect knowledge of a system's wave function, the theory yields only the likelihood of different results, never a guarantee. This probabilistic nature of quantum events has led some to argue that the universe is fundamentally random at its core, challenging the hope for a fully deterministic cosmos. This profound indeterminacy has sparked rich debates not only about the nature of reality, but also about the limits of scientific inquiry. Some have speculated about superdeterminism, a hypothesis that would restore determinism by assuming correlations between hidden variables and the choices physicists make in setting up their experiments. Yet, the prevailing consensus among physicists is that quantum mechanics has done more than any theory before it to shatter the idea of a clockwork universe. It has mapped out hard boundaries, edges of knowability, beyond which questions cannot be answered, not just for technical reasons, but because nature itself refuses to yield. As quantum theory continues to evolve, it reminds us of the humility required in the pursuit of knowledge. The quantum realms do not simply challenge our methods, they force us to confront the possibility that some questions about the fabric of reality may forever lie beyond the edge of what can be known. In this strange and beautiful domain, the limits of knowledge are not temporary but fundamental, a testament to the evolving and sometimes humbling relationship between the human mind and the mysteries of the universe. Imagine, for a moment, standing on a quiet hill at night, gazing up at the vastness of the sky. The stars you see, shimmering and distant, are not merely points of light, but messengers from the edge of what is knowable. Their light began its journey toward your eyes long before you were born, perhaps even before humanity existed. Yet, as grand as this vision seems, the cosmos withholds far more than it reveals. The universe itself, by its structure and the laws it obeys, draws boundaries around what physicists can observe, measure, and ultimately understand. At the heart of these boundaries lies the speed of light. This universal constant is not just a cosmic speed limit for racing photons. It is the fundamental cap on how fast information, matter, or energy can travel. No signal, no material object, no whisper from a distant galaxy can exceed this velocity. The constancy of light speed is enshrined in the very foundation of modern physics and shapes the way cause and effect ripple through spacetime. If you could somehow send a message faster than light, the sequence of events could unravel, turning causality itself upside down. The universe, it seems, has decided that some places and moments are forever out of reach, no matter how clever our instruments or how powerful our telescopes. These limits reveal themselves most dramatically in the concept of cosmic horizons. The universe is not only immense, but also in constant motion, expanding, stretching the very fabric of space. The cosmic horizon marks the ultimate edge of our observational reach. It is the farthest distance from which light has had time to arrive since the birth of the universe. Beyond this horizon, galaxies and phenomena exist, but their light, racing at the fastest speed allowed, has simply not had enough time to reach us. In effect, the observable universe is a bubble, and we are at its center not by cosmic privilege, but by the inescapable math of time, distance, and light's unwavering pace. Physicists distinguish between a couple of different horizons. The particle horizon defines the maximum distance from which any signal could possibly have reached us since the beginning of time. It is, in a sense, the outermost layer of our cosmic knowledge, set by the age of the universe and the relentless march of light. Then there is the event horizon, a subtler, more haunting boundary. This marks the limit of what can ever be observed, even with infinite time. Because the universe's expansion is accelerating, there are objects now visible whose light, emitted today, will never make it to us in the future. They are already slipping away, receding faster than the speed at which their light can bridge the growing gulf. In time, entire galaxies will fade from view, not because they have ceased to exist, but because the universe has swept them beyond our reach forever. This cosmic censorship is not just poetic, it is a hard fact that shapes the ambitions and frustrations of cosmology. Even our most sensitive detectors run up against a final wall, the cosmic microwave background, or CMB. This faint afterglow is the oldest light in the universe, a relic from a time when the cosmos was just 380,000 years old. Before this epoch, the universe was so dense and hot that light could not travel freely. It was trapped, scattered among a fog of charged particles. The CMB marks the edge of transparency. Look further, and the universe becomes opaque. This radiation, faint and cold but omnipresent, is the farthest signal we can ever hope to detect, serving as a screen that hides the universe's earliest moments from direct observation. Despite these formidable barriers, physicists continue to push at the boundaries, mapping the CMB in exquisite detail, probing the faintest galaxies before they vanish beyond the cosmic event horizon, and building ever more sensitive instruments. Projects like the Simons Observatory are dedicated to squeezing every last clue from the ancient light that washes over Earth. Yet there is a growing recognition that these efforts, as heroic as they are, face limits that no technology can ever overcome. The expansion of the universe will eventually push distant galaxies beyond detectability, and the cosmic microwave background will remain, forever, a veil drawn over the universe's first act. These cosmic boundaries remind us that even the grandest scientific ambitions are shaped by the structure of the cosmos itself. The universe is not an open book, but a story with missing pages, some torn away by the speed of light, others erased by expanding spacetime. The limits of observational cosmology are not simply technical problems to be solved, but fundamental features of reality that define what can, in principle, be known. In embracing these boundaries, physicists are not admitting defeat, but instead acknowledging the universe's profound complexity, a complexity that, paradoxically, makes the pursuit of knowledge all the more meaningful. Physicists have always been explorers, peering into the structure of reality with unrelenting curiosity. As we reach the end of our audiobook journey, it becomes clear that the further we travel, the more we encounter boundaries, some imposed by the universe, others by the very tools and concepts we use. These limits do not diminish the scientific quest, instead, they enrich it with nuance and mystery. The landscape of physics is filled with profound questions, many of which remain unsolved despite centuries of effort. Dark energy, the arrow of time, the nature of chaos, and the fundamental incompatibility between quantum mechanics and general relativity are not just technical puzzles, but deep mysteries that hint at the edges of human understanding. The process of doing physics is more than collecting data or writing equations. At its heart lies an ongoing interplay between theory and experiment, a dialogue that is sometimes harmonious, sometimes challenging. When physicists set out to probe the unknown, they do so with models in hand, but also with the awareness that every experiment is shaped by the limitations of measurement, the structure of information, and the boundaries of what can be observed. Recent research has brought these issues into sharp focus, especially in the context of quantum precision. At the most fundamental level, experiments are bounded by what is called the quantum Fisher information. a mathematical expression that sets the ultimate limit on how much can, even in principle, be learned from a quantum system. No matter how ingenious the experimental design, nature draws a line that cannot be crossed. But limitations are not confined to quantum mechanics. Information theoretical boundaries pervade all of physics. These arise when physicists attempt to choose between competing models, or when they confront systematic discrepancies that stubbornly resist resolution. The process of model selection is more than a technical task. It serves as a reminder that every scientific framework is provisional, defined as much by what it cannot explain as by what it can. Some discrepancies may be resolved with better data or more refined theories, but others might point toward fundamental gaps in our understanding, gaps that no amount of precision or ingenuity can bridge. As experiments achieve ever greater precision, new questions emerge. What actually counts as an experiment, and where do its boundaries lie? Researchers have begun to examine the very definition of experimental knowledge, considering whether there are forms of inquiry that lie beyond the reach of empirical investigation. There is a growing recognition that some aspects of the universe may be forever beyond direct access, not because of technical shortcomings, but because of intrinsic limits built into the structure of reality itself. Despite these formidable boundaries, physics has a long history of surprises. Paradigm-shifting discoveries like the detection of gravitational waves or the realization that the universe's expansion is accelerating have often emerged from the interplay of bold theory and meticulous experiment. History teaches us that the unknown frequently harbors phenomena that challenge our expectations and force us to revise our understanding. The next breakthrough may come from the detection of new particles, the unraveling of dark matter, or perhaps from an unexpected corner of theory or observation. Physicists anticipate such surprises, knowing that the greatest mysteries are often those that lie just beyond the reach of current knowledge. Yet, for all its triumphs, physics remains marked by enduring questions. The list of unsolved problems is long and humbling, encompassing everything from the nature of space-time to the ultimate fate of the cosmos. Some of these questions may be inherently unanswerable, at least within the framework of current science. Others may require not just new data, but new ways of thinking, shifts in perspective that are as much philosophical as they are scientific. It is here, at the intersection of physics and philosophy, that the quest for knowledge finds its most profound expression. Philosophers and physicists have long debated the nature of space, time, and physical law, as well as the meaning of explanation and understanding itself. Philosophy has played an essential role in clarifying concepts, guiding inquiry, and challenging assumptions. Far from being an abstract pursuit, philosophical analysis has practical consequences for how experiments are conceived, how theories are constructed, and how evidence is interpreted. Many scholars argue that science and philosophy need one another, especially as physics confronts questions that resist straightforward answers. Some thinkers suggest that physics is now reaching a stage where its greatest challenges are as much philosophical as empirical. The premise of an objective world, while central to physics, remains the subject of ongoing debate. Can we ever achieve complete knowledge of reality, or is the universe, in its deepest essence, forever shrouded in mystery? These are questions that may never be fully resolved, but they give the scientific enterprise both its humility and its grandeur. In the end, the quest for knowledge in physics is not a straight path towards certainty, but a winding journey through wonder, doubt, and discovery. The limits of knowledge are not failures, but signposts, reminders that the universe is richer and more mysterious than any single theory or experiment could ever capture. As we look to the future, the enduring mystery at the heart of the physical world is not a barrier but an invitation, an open horizon that beckons each new generation of physicists, philosophers, and curious minds to ask, to explore, and to dream.